Modern digital security rests on one mathematical assumption. Factoring large prime numbers takes classical computers too much time. That assumption is now failing. The development of quantum decryption capability means the algorithms protecting global financial, military, and intelligence networks will soon be transparent. We are approaching the post-quantum cryptographic threat, a specific vulnerability horizon where current encryption standards fail, rendering decades of legacy data vulnerable to retroactive decryption. This chart illustrates a simultaneous crisis. The vertical axis tracks exponential AI compute demand, while classical hardware efficiency hits a physical limit. The point where demand exceeds silicon efficiency and decryption breaks encryption marks the quantum inflection point. National resilience in the quantum age requires a total shift in secure infrastructure to prevent the wholesale collapse of state-level encryption. Addressing this challenge shifts the priority from isolated research projects to a centralized national infrastructure model. This requirement is the basis for Alium. Led by Umair Abbas, it is the nucleus for sovereign quantum infrastructure, combining atomic-level stability with continuous intelligence. Alium operates as an infrastructure of quantum authority, or IQA. It functions as a single integrator for statecraft, capital architecture, and advanced applied physics. Fragmented approaches, such as focusing only on hardware fabrication or treating AI as a secondary software feature, leave gaps in the secure data pipeline. The resulting architecture is a 5-layer integrated stack, building from individual photons up to geopolitical policy. Layer 1 is the physical layer. Secure communication begins at the subatomic scale through the generation of entangled photon pairs. The primary mechanism for this is spontaneous parametric downconversion, or SPDC. This process splits a single photon into 2 entangled photons with perfect correlated states. This fiber cross-section illustrates layer 2. Entangled particles establish secure links across hundreds of kilometers. The challenge is signal attenuation. As photons scatter, the entangled state degrades. To solve this, quantum repeaters deploy trapped ion memory to catch the fading signal and restore the connection. This transmission is further stabilized using error correction models, such as bosonic codes, ensuring the entanglement remains fault-tolerant regardless of environmental noise. This physical integration creates a nationwide quantum key distribution backbone. It renders defense and central bank communications mathematically tamper-proof. Layer 3 is the compute layer. High-performance computing is scaling toward a hybrid model, utilizing classical supercomputers for standard processing while offloading complex variables to quantum hardware. This routing hub visualizes the orchestration engine. It analyzes data streams in real time, routing standard workloads to classical clusters and complex problems to quantum units. This optimizes for speed and latency, merging the outputs back into a single compressed feed. Powering this layer requires integration with superconducting QPUs and scalable trapped ion arrays. To maintain security, these compute fabrics run within air-gapped enclaves, fed directly by the secure backbone established in Layer 2. Controlling this sovereign hybrid cloud allows a state to execute advanced processing internally, removing the necessity of exporting sensitive data to foreign manufactured hardware. Layer 4 is the intelligence layer. The challenge here is adapting machine learning models so they can effectively train on the hybrid compute fabric. Alium employs hybrid algorithm design. This means engineering neural architectures that are natively structured to utilize quantum states from the ground up. This requires implementing specific mathematical tools, primarily variational quantum eigensolvers, to stabilize gradient estimation during the training phase. Native quantum AI accelerates molecular simulation, optimizes energy grid distribution in real time, and advances cryptanalysis capabilities for defense. Layer 4 channels raw hardware processing into directed intelligence acceleration, allowing host nations to model complex global systems faster than classical algorithms. Generating this volume of computational power introduces massive operational risk. Layer 5 is the governance layer, built to control and safeguard the technology. This pyramid outlines the classified innovation segmentation model. Base Tier 1 covers open research and civilian AI. Tier 2 designates controlled dual use, limiting restricted hybrid AI systems to vetted partners. Peak Tier 3 is strategic classified. restricting quantum cryptanalysis and entanglement networks to national oversight. The governance layer enforces ethical AI compliance, implements zero-trust architectures, and dictates strict export controls on hardware components. Without an enforced policy framework, the physical networks and AI layers below become liabilities, open to weaponization by rival states or internal actors. To measure the success of this deployment, strategists use the Geopolitical Quantum Competitiveness Index. This evaluates a nation across 5 pillars: research depth, infrastructure, security integration, capital investment, and diplomatic influence. A nation standing on this index over the next 25 years will determine which of 4 grand strategic scenarios it will inhabit. The most severe operational failure leads to Scenario D, technological dependency. This is defined by an incomplete migration to post-quantum cryptography and forced reliance on foreign quantum processors. This timeline contrasts that dependency with the target objective, Scenario A, quantum dominance. Here, a nation secures a sovereign quantum backbone and establishes global hardware standards. Executing Scenario A requires a phased timeline, building regional innovation hubs within 10 years and scaling into a nationwide entanglement network by year 20. In the post-classical era, technological dependence translates directly to strategic vulnerability, making Scenario A the only tenable objective for a sovereign state. Financing the Alium stack requires a blended capital approach of sovereign wealth funds and strategic infrastructure bonds mapped against a 25-year return horizon. This is the mandate of Alium, Advanced Learning Intelligence Universal Methodology. The platform acts as the functional bridge between subatomic properties and the governance of digital intelligence. As these nodes connect, they form a post-quantum global network where secure communication channels and hybrid compute hubs are governed by allied standards. By linking applied physics with international diplomacy, Alium establishes the baseline for future sovereign power.